Hello, and welcome to a joint webinar from Expedera and Andes entitled Optimized Chip Design with Main Processors and AI Accelerators. During today's session, we will be presenting a series of slides followed by a live Q&A. If you have questions about content presented, you can use the questions widget within the webinar tool. We will aim to answer as many of those questions as possible. However, if we're unable to answer a question during the live session, we will follow up with a personal answer to you via email. Let's get started with an introduction. My name is Paul Karazuba. I'm the Vice President of Marketing at Expedera. My background is in a variety of semiconductor technologies, including computational and optical imaging, interfaces, and silicon device security. Prior to Expedera, I've worked in marketing at PLDA, Rambus, QuickLogic, Micron, and Foveon. John?
Yeah, thank you, Paul. My name is John Min. I'm the Director of FAE at Andes. I've been around microprocessors for the last 30 years, including CPUs, DSPs, and custom processing ASICs. Before Andes, I was in CPU companies like MIPS, ARC, and Sci5. I've also worked in consumer electronics at LG and HP. And I have multiple degrees from University of Southern California. Go Trojans. Next slide, Paul.
Thanks, John. Let me take a brief moment to introduce Expedera. Expedera is an AI accelerator startup based out of Silicon Valley, specifically Santa Clara. We've developed a revolutionary approach to deep learning acceleration since our founding in 2018. We exited stealth mode in 2021 with the public reveal of our packet-based Origin DLA architecture, which I will very briefly talk later about in this talk. Most recently, we announced our Series A funding round. Our patented AI acceleration solution offers an industry-leading IPS per watt and IPS per millimeter, ensuring our customers receive the optimum IP for their price, performance, and area constraints. While we are a startup and our product is IP, we're silicon and field proven. Our first large-scale customer, a leading worldwide handheld consumer device maker, is in production with RP, and we have deployed in a number of leading-edge process nodes. The team comes from some of the best-known companies in the industry, with a strong background in neural networks, ASICs, AI, and imaging. John, tell us a bit about Andes.
Yeah, so Andes Corporation is a pure-play CPU IP company. So we specialize in CPU IP, and that's all we do. We're a 16-year-old public company based in Taiwan, and we have been involved with RISC-V from the beginning for about 6-7 years ago. We are active in RISC-V International, running task groups and technical steering committees and board of directors. And of course, with this, we're very active in a major open source community. The company-wise, the founders have over 100 years of experience in various companies in Silicon Valley. Companies are 80% engineers with offices worldwide. We have over 250 licensees with over 20,000 active users of our software and the site software development tool. Last year, we surpassed 10 billion chips shipped with our IP, majority of which are RISC-V containing IP. Paul? So let's talk about CPU in a sense. This will set up a foundation. CPU has many instructions, and then with RISC-V, there's extensions where we could put in floating point operations, different multiplier operations, DSP, vector, a lot of ways to expand the CPU. And then, of course, the natural extension is user extensions, where you are allowed to create new instructions, new ports to customize these processors and attach a tightly coupled coprocessor to the main processing engine. Now, this is the engine. It's very flexible, programmable, software-driven engine. Sort of corollary to that is if you know a specific function you want to do, you might be able to design and work with the external hardware accelerator like what Expedera is offering. Next slide. So containing all this flexibility in software, Andes makes a variety of CPUs in different performance levels and different features. We start with N22, which is our basic fundamental microcontroller. And then on the microcontroller line, we go up the performance to 25 series and 45 series. To these base processors, we will add DSP capability, vector processing capability, and floating point capability to have more signal processing performance. And on top of that, we have single core, multi-core versions of Linux capable processors. So now you could run Linux for user applications, multi-cores to create a true computing environment. And you could choose one or more of these processors to either do housekeeping, signal processing, even neural network acceleration, or even to run Linux user interfaces. So let's see how this works with Expedera accelerators. Paul?
Thanks, John. A real question people ask is, why there's so many different processor types in the market today, whether they be a CPU or a GPU, a VPU, a DPU, and an NPU. For reference, let's just call those XPUs for right now, where X is the variable. The answer really boils down to the fact that as computing technology has advanced, heterogeneous computing has become a necessity. An AI accelerator, like from Expedera, can be seen as a coprocessor. It sits next to a CPU and offloads some of the functions. Heterogeneous computing has grown as frequency scaling died out more than a decade ago, and we've obviously hit a power wall. And while homogeneous or multi-core computing can increase performance, unfortunately, it also increases the power consumption. So if one thing you could take away from here is certainly, as John will tell you, a CPU is certainly capable of handling the functions that a GPU or an NPU, or neural processing unit, would do. But that doesn't necessarily mean that it's the best place to do it. And that's something you're going to hear us talk about during the talk today. Heterogeneous computing can increase the performance more dramatically and make it much more efficient, often by orders of magnitude. So examples of heterogeneous computing can be illustrated using die shots of various high-end CPUs that we're showing here. I'm highlighting the approximate area of each of these dies that's used for AI acceleration. And again, these areas are approximate only, but from them, you can certainly see how the AI engine takes up a good portion of the silicon, but not the majority. High-end chips have already deployed multiple XPUs on chips, and we expect this trend to very quickly push into mass market chips. I won't bore everyone listening with the various AI market forecasts. Even a cursory review of the most conservative 10-year outlook for AI shows that it's going to be deployed into architectures from the largest data centers to the smallish edge nodes, from your mobile phones to your edge devices to your automobiles. So let's talk about where and how AI is deployed today. This graphic demonstrates the where and how of where you'll find it. On the edge, today's AI algorithms are typically within the CPU. This would be expected, as AI deployments on the edge typically have a comparatively very low processing requirement, and thus don't generally consume a lot of power, which is obviously extremely important for any edge device, especially when you consider battery-powered edge devices. As you move to the enterprise edge, you start to see the emergence of dedicated AI processors, the NPUs that I had mentioned earlier. As we move from edge to data centers and appliances, we see a whole assortment of AI deployment methods, from CPUs to GPUs and even FPGAs. So if there's one takeaway from this chart, it's that there is no standard way of deployment of AI algorithms, which brings us to the question. CPUs and dedicated AI accelerators, are they friends or are they foes? And which is the right platform for running your AI algorithms? So John, let me pass it to you here.
Okay, so personally, I see it as a friend, but friends need a personal space as well. So question is, if CPU could handle the AI workloads, but should it? Where do we use CPUs today? SoC management, setup configuration of any IP, including an accelerator. Data pre and post processing or data formatting is very important. Maybe the accelerator works 100% efficiency if data is pre-processed, and CPUs are good for that. And then you could use CPU for future proofing. There might be new models that the accelerator may not be as efficient, um, or perhaps entry-level AI where you're doing a very low low performance AI kind of application like keyword spotting, or very high performance AI engine assist. So CPU can be used in a variety of applications. Now the accelerator, on the other hand, is optimized and dedicated to a specific or set of neural models. We'll need a CPU or a simple state machine for management, setup, data movement, and that kind of applications. It will most likely have dedicated compute bandwidth. It's only going to do those AI models. And then it's pre-programmed, and it is a high-performance engine that CPU could help with. Now, rule of thumb, where should you start looking at a CPU versus accelerator for neural network applications? From about 10 to 50 gigaops is the sort of range you want to look at. If you're closer to 10, start with the CPU. If you're closer to 50, maybe you start with the neural net accelerator and what's needed. Idea is you want to optimize power to the performance area what you need. Next slide, Paul.
So John, I really like how you put that. CPUs and AI accelerators are definitely friends, but need their own personal space. I think that's a quite good way of saying it.
Yeah.
So in a bit of a preview of the second part of this webinar series, which you can pre-register for again using the link within the webinar tool, let me talk about some of the questions that we believe a chip designer would need to ask themselves when considering how they should deploy their AI algorithms. Let's first look at the question of what the actual AI use model is. And by model, I'm not necessarily speaking of a ResNet or a YOLO model, for instance, which obviously needs to be considered. But rather, I'm speaking more of the question of what is the exact use model of AI on my chip? And let me give a few examples of that. So one question to ask is, my AI algorithm something that's going to be always on, or is it only going to be something that's going to be used sporadically? Let me give an example of that. Let's say you were deploying AI into a security camera, and the use model of security cameras obviously is that they are typically always on. And if that AI algorithm was, let's say, looking at the body language of people within the scene to try to understand, let's say, if there's aggressive parties in the scene, perhaps creating trouble, your AI model is going to be always on there. And that would be something that you would absolutely want to consider in making the choice of CPU versus AI accelerator. And on the flip side, is it only going to be used sporadically? Let's say your AI model is just simply noise reduction, audio noise reduction in a system. And let's say the audio portion you're only forecasting to be active, let's say 0.5% of the time. Obviously, the power consumption of that on your system is going to be significantly less than what it would be for the always on example. And that's something that the chip designer would need to consider. You also need to look at your performance requirements, average and peak. Is your AI algorithm something that's always going to be running and pretty consistent from minute to minute or hour to hour? Or will there be times where your AI model is really going to peak? And do you need to account for that performance from a processing and a power point of view? And then once you've got the performance portion of PPA, again, power, performance, and area, you do also need to look at the others, the power and the area. And you need to determine what your budget for those is as well. NPUs and dedicated AI accelerators are going to allow generally much more favorable power consumption versus running those same algorithms on a CPU, but it's done at the cost of silicon area, obviously. Placing another processor next to your CPU is going to grow your chip. Question a system designer needs to ask themselves is growing the chip and increasing the cost, the manufacturing cost, is that going to be acceptable for my program needs? Or does the power and the performance rather mandate that I have to do that? there's lots of things, questions that needs to be answered. Of course, you've got your development or your IP acquisition costs. Certainly the AI engines don't come for free. Do I have the actual budget for that? And I'm going to further complicate this decision. Let's look at the reality of AI applications. AI development from an algorithm point of view is far outstripping Moore's law. And that places some very unique burdens on chip designs and product managers. What I mean by that is because these algorithms are advancing so fast, people designing the chips and the people managing those programs have to anticipate that algorithms and trained neural networks that don't exist today are going to have to be used on their chips in the future. And even today, AI compute is already limited by the power consumption of CPUs and GPUs. Leaving chip designers struggling to determine the best way to deploy AI in their chips in a PPA-friendly method. So there's lots of questions that one needs to answer. So, perhaps let me sum up this portion of our remarks with this. In a situation where a CPU can theoretically provide the necessary PPA for running an AI algorithm, the question of whether or not to use an AI accelerator will probably come down to cost. And given that heterogeneous computer is faster and more efficient, there's going to be a performance point where the choice to use an accelerator is clear cut. And John had mentioned that earlier, the numbers of 10 to 50 gigaops, and I absolutely would agree with those numbers. Below that, a CPU is likely going to provide a cheaper, simpler, and potentially more flexible solution. But once the decision to use an accelerator is made, I would absolutely caution you to be sure to choose the one that offers the right power, performance, and area requirements for your needs. So before we open this up for a live Q&A, if you could humor us and allow John and I just a very brief time to give introductions to our products. So John?
Yeah, thank you, Paul. So at this advantage, we talked briefly about different processor options we have. We have something a little more. So in this course, our standard RISC-V instruction set, and with a little bit of Andy's magic and these extensions in them. So there are more instructions than standard RISC-V. We're superset. And then we have the other technology that makes it even better. So we have ND-V5 instruction set includes hardware assist, security, and power options like stack safe that has a hardware supported stack protection mechanism. Hey, what if we could catch stack overflow before it happens? And then power options like power break, which is software controlled power usage and performance. You could, by software, dial up or dial down processor performance, thereby dialing in the right level of power usage. Quick nap, go to sleep. Let the CPU go to sleep, but keep the cache contents, retain the cache contents so you could do a quick wake up. So we have all these extra technologies on top of just standard CPU. And lastly, what we really have is called ACE custom extensions. We call it ACE. This is where you get to create your custom instructions, your own memories and ports to create a super instruction that accelerates your algorithms. Next slide. So let's talk a little bit about ACE. So it's just more than just instructions. So neural net accelerators, one of the challenges more is data movement as well as computation. So we could have custom instructions to create, accelerate computation, and then we have custom ports or custom memories to feed that engine quickly and efficiently, and then be able to talk to an external accelerator like the Expedera accelerators. Paul?
Thanks, John. Very briefly, a quick introduction to Expedera's deep learning accelerator. It is based on native execution and leverages networking architecture principles. What makes us fundamentally different from other AI accelerators on the market today is the fact that we don't simply process a trained neural network layer by layer. Instead, we use packets as a work unit, which solves complex hardware and software. Our compiler is co-designed and optimized for our deep learning accelerator. allowing us between a 70 and 90% utilization of our processor compared to, let's say, 20 to 40% of what typically might be found in an AI accelerator. Our single core will scale to 128 TOPS, obviously well in excess of the 10 to 50 gigaops inflection point that John and I had mentioned earlier, and certainly multi-core scales to petaops and beyond. We like to say, and third parties have shown, that we have the highest TOPS and inferences per second per watt and per millimeter squared. And of course, we're patent protected. And I did mention those third-party sources. You can contact me using information that you'll find here in the webinar to get more information on this. But we like to point towards third-party market reports that back up our claims. And in this particular case, running a ResNet 50 network, if you look at inferences per second per watt, our accelerator core is far outstripping the performance of our competitors. So with that, we're about to open it up for a live Q&A. If you do have questions, please insert them to the widget on the screen. We'd also like to take this time to invite you to join us for part 2 of this webinar, Designing for the Future, Important Considerations for Specifying a Main Processor in AI Accelerator. Again, you can register using the link in the webinar here by scanning the QR code on the screen, and you'll also receive an email about this. If you do have any questions direct for John or myself, you can reach out to us at the emails on the left-hand side of the screen. And with that, we'll open it up for live Q&A.
Hi, everyone. If you have questions, put them in the question window. And in lieu of that, I'll begin with some questions we've already received. Can you provide an example of an AI application running on your CPU?
Okay, well, this is a great question. So as we mentioned during the webinar, CPU is flexible enough, it could do everything. But maybe the problem is not it can do it, is can it do it quick enough? So let's take a couple examples. There's this on the home security devices. There are things like keyword spotting or security device like movement. Those type of applications where my security camera is looking at the field of view of my driveway. I want to activate the alarm if it's a person versus a dog or a cat. So those are common simple activity. Keyword spotting is also a great application of AIs that the CPU is ideally designed to handle.
Okay. Here's another one. What tools are available for optimizing AI software and algorithms?
Okay. 2 ways. And then the CPU side, we have a CPU software optimizers, profile viewers, and we have this great tool called Clarity, which looks into the pipeline of the vector engine to say where the stall's coming from, data dependencies. So we have many tools to optimize software, AI software, and vector software altogether.
Okay. All right. Now, another one. How do you choose a full-featured CPU running slower versus something simply running the simpler CPU faster?
Well, it's a common trade-off. So you could throw more gates or more area at a problem. You might be able to do it faster, but the problem with that is unless you're using 50, 60, 100% of the time, some of those gates are going to be not used and just taking up power. So profiling your software is very important, and to find out the usage. If CPU is going to run 100%, maybe even more, think about an accelerator. If you're doing AI, probably once every 10 seconds, once every 5 seconds, then perhaps CPU running low speed, more features might be important. So it's a many trade-offs. I guess as a job security, I help customers make those trade-offs.
Okay. Expedera, what is the differentiation that you bring to the market? Because there are a number of startups out there.
It's a good question. Let's start with the primary sort of differentiation is we've taken a fundamentally different approach to AI acceleration, and a lot of that comes from the networking background of our founders. Rather than take a CPU-centric approach to neural network processing, we have taken a network-centric approach. We mentioned earlier that we segment the neural networks into packets. Packets are essentially command streams that can be efficiently scheduled and executed by our hardware in a fast, efficient, and deterministic manner. Additionally, our co-design approach enables a simpler software stack and a more productive and system-aware design and development experience. I don't want to go too much into detail on this. I will say that there is another webinar on the Expedera channel here that goes more into detail on packets, as well as a white paper that you could download from our website. But maybe answer this question a little differently also by saying, we provide highly efficient AI inference solutions that are customizable. If our customer needs deterministic performance or a guaranteed level of performance with the best power and area efficiency, we can do that. If they need flexible, future-proof solutions that can handle mixed models, we can do that too. That's one thing that also makes us different, is the ability to have an almost unlimited number of degrees of freedom in the way that we deploy our engine that allows the customer to really dial in their power, performance, and area requirements.
Okay. All right. How would Andes and Expedera approach a common customer together?
Geez, there's a lot of ways to answer that question. I would first start off by saying, Expedera's product is IP. You're always going to integrate IP into a chipset, which is always going to include a GPU or a CPU or an apps processor or whatever it may be. Working with customers to integrate to a CPU is, and pardon the simplicity of this expression, but it's really just another day at the office for us. And I mean that only really in the best of ways. Tasks and activities for us are a very routine occurrence that we've done many times before and will do many times in the future.
Okay. Don, you want to add anything to it?
Yeah, it's I echo what Paul said. And if you're answering from the technical approach, most customers have architects who understand how much CPU load they need, how much the accelerator load they need. However, since there are overlap, you could have a powerful CPU for a slightly less powerful accelerator, or vice versa. Working with customers during evaluation phase, benchmarking, and really defining customers' needs is important. You're going to need a CPU, most likely for higher applications. You need an accelerator. Question is picking the right ones for your power, area, and performance needs.
Okay. There's a question that came in. Just what happens to a new AI model or variant is needed with a neural network accelerator? How do you sort of support that well?
Yeah, that's an interesting question. There's two ways to answer this question, and I don't know if the person asking was specifically talking about the introduction of a new model pre-silicon or the introduction of a new model post-silicon. So let me look at it both ways. Pre-silicon, let's just take it in a logical order. The short answer is, we issue a new IP cut to a customer. Obviously, one of the great advantages of IP as a unit of commerce is there's an ability to change that IP much quicker than the requirements, much quicker than the timeline it would take to change a chip, for instance. Supporting new models for us is a matter of days in some cases, not months or years as it would be in a chip. But let's also look at post-silicon. So a situation where our customer has taken Expedera IP, has deployed it in their chip, has taped out the chip, brought their chip to market. The short answer here is, our DLA, our deep learning accelerator, is programmable. And if the DLA supports the underlying math operation of the new layer or model, we can effectively program this on top of IP that's already out there. The scope of this is purely software. And it's even to the point with our product where our customers can even define new operations using our software without even needing to involve us. We're always happy to help, but we do have some instances where customers prefer to do the deployment themselves, and we're happy to support that.
Okay. I have some other questions here, and I just want to make sure that we haven't already answered them. I've been so concentrating on questions, I haven't noticed what the answers are. Are there tools to convert models running on NVIDIA, library conversions?
John.
Yeah. So there's some open source tools, and some of these models actually, whether there's TVM or other models, fundamentally the models are more open source generic. So a lot of the software can be ported over. There's some open source tools. There's some proprietary tools that could help that conversion.
Okay.
Great.
Oh,
So
I think we've ended the questions. Yeah.
Yeah. So it looks like we're actually running short on time. So thank everyone for joining us. As mentioned, there's going to be a part 2 of this webinar. You can register for that using the link provided. John and I's contact information additionally was in the presentation here. If you'd like to get in touch with us, please feel free to reach out. Thank you very much for your time and have a great day.
Thank you, everyone. Have a great day.
Thanks.